Okay, so with the usual 5 minutes late and with Michaela permissions or perhaps order, I don't know, it depends on the interpretation, we can begin this session. So it's a pleasure to have Peter Jipsen, that does not came from very far, here from Chapman University, but this does not diminish the pleasure, on the contrary, and the structure of some residuated lattices. I think that even if it is wish to be a presentation a little more technical than the other, we can maintain the same policy. So if there are clarification questions, they can be asked during the talk. And if not, for more general question, we wait for the final discussion. Okay? Okay, so if we all agree, Peter, the structure of some residuated lattices.
Thank you very much. It's an absolute pleasure to give a talk in this seminar. And I'd just like to say right from the beginning that I've structured this talk to have all the definitions in there so that it might be accessible to people who have not heard about what a residuated lattice is. But of course, there will be a lot of details, and so there's a lot of slides, and you should think of it more like a movie. The details are not as important as the story, and I hope it's interesting. So, yes, I did change the title a little bit. Perhaps you noticed I put the word "sum" in there because when I did put the talk together, I realized it was too much. My abstract was too ambitious, and so I'm only talking about some of the results I wanted to say. But this is the idea. I'm going to motivate the structural results in algebra by looking briefly at groups and motivate the residuated lattices by considering relation algebras a tiny little bit. And then I will construct various residuated lattices to show how we understand some of the structure of these, of certain types of lattices, residuated lattices, much better now than we did, say, 20 years ago. And so the components that we use to build the various ones from simpler stuff, I mean, the components themselves might not be so simple, but we can choose them to be very simple, and then what we build is also well understood. Or sometimes we can only decompose stuff into components that themselves are still a bit mysterious, but at least we know how to build things after that. You know, or if we then understand the components, we will understand everything. And the constructions that we use are various ones. There's just a list. I'm only going to look at the direct products I'll briefly mention, and they are a very basic way of doing things. The concept products and the more recent use of Plonker sums are the projects that I want to mention and that I've been involved in. And ordinal sums are a very nice way of building things that are a special case of concept products. And nuclear images and co-nuclear images are interesting, but not necessarily interesting to physicists for the name's sake, but just because they are very useful, and I wish I could say more about them, but I'm not going to. So now we have this quote here. Die ganzen Zahlen hat der liebe Gott gemacht. Alles andere ist Menschenwerk. This is a famous quote by Leopold Kronecker. I'm not sure if he exactly said it this way, but this is how it's commonly reported in German. When it's translated into English, the last word is often the work of men. And I just wanted to point out that that is not the correct translation. So starting from...
Are you sure of the translation or the German of the translation?
I made the translation correct by putting the word that he actually said.
Yeah.
And if you look the translation up in English, the last word is men.
So you are sure of the German then?
Yes,
the German is
German translates into human.
He's a native speaker of German.
Okay, good. That's what I understand.
But I'm not sure whether he said exactly those words. I wasn't around, but it's a famous quote that's attributed to him. And so we're going to start there. The integers, humanity, noticed that these operations on the integers have these 4 very nice properties. And I'm only concentrating on the addition now. So these properties are known as associativity. You can put the brackets wherever you want. for addition. The commutativity, you can switch it around, and you have an additive identity, which is 0, and then you have this additive inverse. And those 4 properties are nice. And then Dedekind said,
sorry, are you sure that with Gans it was meaning relative and also the negative?
This is a debate. But in English, I mean, in German, ganze Zahlen, sie for the integers.
Yeah.
And ganze means the whole numbers. So in German, in English, whole numbers can mean the positive whole numbers. Could mean the
it is certainly true today. I'm not completely sure that it was true at the time of Kripke.
Yes, but I will get to some other results, and then we may have an opinion. So in this point of having recognized that a structure that is fundamental to mathematics has some nice properties, we should abstract from them. This is Dedekind's point, that the greatest and most fruitful progress in mathematics and other sciences is through the creation and introduction of new concepts, those to which we are impelled by frequent recurrence of compound phenomena, which are only understood with great difficulty in the older view. So what kind of phenomena? Well, in this case, the phenomenon of a group. And the point is that a group is a structure, a mathematical object that has a binary operation, a unary operation for inverses, and this element E, which satisfies 3 of the properties that were on the previous page. And we call the group commutative if the binary operation also has the commutativity property. The operation has changed to be a dot so that it looks less like the standard addition, but of course now it looks like multiplication. And of course, the integers are an abelian group. Abelian, yes.
Do you happen to remember when Dedekind said that?
In the 1860s, I'm not sure. I should look it up. I didn't. No, I don't. But it's crucial because he's also involved. Later we get to lattices, and he proved one of the nice results about finite lattices. So he's definitely one person who did this vehemently. The concept of ideal, of course, is where the abstraction was most prominent, and probably where he saw all this. He's known to have really struggled with getting things right in his papers and having revisions after revision to get it exactly nice and changing it. The real numbers are another group. There are many abelian groups. You can take the non-zero real numbers with multiplication and inverses and the number 1. And here, this is a very important group, or range of series of groups for every integer n. You get the cyclic group with n elements, and with this operation, which is modular n, but you can define it without talking about divisibility or remainder, just directly. It's very concrete. This is highly finitistic stuff. And you can build larger groups from these finite groups by taking direct products, which are really simple. You just take the base set for the group to be ordered pairs, like little vectors of numbers. And then the operations here are the pointwise operations. And you can do this with any number of copies of a group, not just a finite number. So you can make huge groups out of finite groups. You can even use larger and larger finite groups and make interesting groups that have internal structure that isn't reflected inside the finite groups. Even in the abelian case, there are some open problems about infinite abelian groups, but finite abelian groups, how many finite abelian groups are there? This is completely answered by a result of Wilbert-Franeker. The fundamental theorem of finite abelian groups says that every finite abelian group is isomorphic to a product of cyclic groups of prime power. You can choose the primes, you can choose the powers, and you will get different groups. So it's really easy to construct and count all the finite abelian groups of a particular size. And if the size is not too large, you can do this by hand. It's not hard. Here's a list of the first few finite abelian groups. And this is remarkable because the theory of groups is these 3 little axioms plus the commutativity. And so we shouldn't have expected this. This just happens to be true. It's a fact about the Platonic universe in which these groups live. And so the list up to size 8, is just these groups. The Z2 plus Z2 is the Klein 4 group, for example. And there's only one group of size 6 because Z2 cross Z3, even though it looks like it's put together in a different way, and that's what the classification says I should have put down there. It's isomorphic to Z6. The fundamental theorem of finitely generated abelian groups, where I'm not actually explaining finitely generated, but it's a much more general theorem, covers a lot of infinite abelian groups, countably infinite abelian groups, because all finitely generated algebras on the finite signature have to be countable. And this was proved by Poincaré 120 years ago. And it's also remarkably simple. It just says you take this finite characterization, structure theorem, and you can add a finite number of copies of Z to get all possible finitely generated groups. And here is the contrast. If you look at commutative monoids, which are really just abelian groups without the axiom for additive inverses, then you take something which is M, the set, an addition operation, which is not normal addition, just any binary operation that is associative, commutative, and it has to have an identity element, which we call 0 here. For example, the natural numbers. It's not a group. Here are the list of abelian groups of particular size. So I showed you by construction all the way up to 8, and you see it even continues in a very simple way. There's only one group of size 10.
Sorry, a linguistic curiosity, because I
Yes.
only wondered, what is in English the difference between monoid and demigroup?
Demigroup?
Semigroup.
Semigroup, yeah. The monoid has an identity element.
The
So it
monoid
has
has
a
the identity
zero.
element.
Yes,
The
or
semigroup are not identical.
it doesn't have to. So it's slightly more general. And
Okay.
in general, people don't study monoids very much because they behave very much like semigroups. And
Okay.
the contrast will be much bigger in the area where we are. But here is the theory of commutative monoids. So the identity element is fixed how it has to behave. That makes these initial numbers a little bit smaller, but then there are so many monoids, even on a small set. There's no structure theory for us to discover here. These things are just crazy. It's like looking at graphs or looking at something that is just a random collection of things. I mean, you can find structure theory for subsets of commutative monoids, certain kind of monoids, but to even show that this number here is 300, I wouldn't be able to do it reliably by hand. And that's sort of my test for whether I understand what's going on. If I can't get up to size 7 of generators or elements, I mean, how can we claim that we know what's happening? But MV-algebras, which I will tell you in a little while what they are way better behaved. They are also monoids with a certain additional structure that comes from an order. And they form residuated lattices. And actually, they're pretty much like abelian groups, and they're even closely related to abelian groups, but not to the finite abelian groups. They are related to certain infinite extensions of these MV-algebras. This is a result due to Mundisi, a categorical equivalence. So they're very, very nice, and we really understand the structure theory of MV-algebras way better than we might have be allowed to expect. The axioms are not as simple as the axioms for groups or abelian groups, but it's very manageable, and it's equally surprising in some ways. They also have lots of applications. And this raises this question, which equationally defined classes of algebras have good structure theory? And how can we find more of them? Because that's where we really can explore and prove more things quite easily, because we can construct things to show that certain stuff happens or doesn't happen, and we can also check our theory against these models. So here's a slide that's good, interesting for the physicists. This is a nice slide I found on the internet. I did not create it. It's to illustrate that the finite non-abelian groups have reasonable structure, or I mean, the groups. Can take out the word non-abelian because in this table of groups, these are the finite simple groups, and they're arranged in a periodic table just as a joke. But this column along the right-hand side are the cyclic groups that we've seen. Those are the only commutative ones in this picture, and they are the commutative groups of prime power, because those are the simple commutative groups.
The green are
The green ones, yes. And then the simple non-commutative or non-abelian groups are the other ones. And there are these groups of Lie type that are basically arranged in these families. They're infinite families. They go across, and then at the bottom you can see how they generate some groups of size Q or much bigger. I mean, the sizes are indicated here. This table can be found. It's a nice poster that we can print. And then there are these sporadic groups. There's exactly 26. That's these down here. And this last one is the monster that was found in the 60s. And then this is the table that shows us that finite simple groups have been classified. They have been characterized. The structure is well understood up to a point, of course. But that doesn't necessarily mean that we understand the structure of all finite groups, because a finite group is not just a product of simple groups, or not just, the finite group is embedded in some combination of simple groups, and so this is very illuminating, but it's not quite the structure theory for finite groups that one would hope for, and it's not easy to say how many finite groups there are on a given size. Like 2048, they were only counted recently, like in the last couple of years by computer, of course, and there's millions of them. And so that doesn't mean that we understand their structure, but we know what they are. And we can find anyone in there, but that's only the finite groups of size 2048. If you go to 2049, assuming that that's prime, it's not. Then, or you go to the lower one, 2047, maybe that's prime. Then we know the structure exactly. It will be in this column that was on the other side. Okay, group theory has many applications in mathematics, physics, chemistry, computer science, you name it. I mean, group theory studies symmetry. Originally, it was invented by Galois to understand the symmetry of the roots of polynomials, and it was permutation groups that he studied. But mathematical objects are connected by structure-preserving maps. Morphisms is the technical name. These things form categories. Category theory is well known now in many application areas. And an isomorph is just a function, a bijective structure-preserving function between two mathematical objects, or two physical objects, or two biological objects. You want to morph one into the other. That's what the function is doing. And thereby you want to transfer the structure of the one object into the other and understand the first one via the second one, or the second one via the first one. That's the idea. Automorphisms are when you do this with maps on an object itself, and that gives you some insight into the object itself. And automorphisms are interesting because the automorphisms of a mathematical structure form a group. That's why group theory is studying symmetry. And the automorphisms of a set are all the bijective functions from x to x, and that's called the symmetric group because it's showing us all the symmetries in the set, which of course are all possible permutations of shuffling stuff around. And then we can say that, well, these groups have, if you start with an L-element set, the group has n factorial many elements. It's huge. And every other group is embedded in such a group for a given set X, because you can take the group itself as the set. And it's a type of trivial embedding. It's often called the regular embedding into the symmetric group, and it's due to Cayley. And it's one of the first results that you learn in group theory. So that doesn't mean that we really understand all groups, but in some sense, if we understood all the symmetric groups, it means we would understand the subgroups to some extent, and therefore we just have to study symmetric groups if we want to. But that's against this principle of abstraction, because symmetric groups are more complicated inside them and how they work. This is just the interface to the applications. The group theory itself should be done.
Oh, can you repeat that? It's not clear the point. Why it is anti-structuralist?
Inside the group theory, you don't have to worry about what permutations look like. And so Studying permutation groups is more difficult, they're bigger. Studying abstract groups, there's very small examples, like the abelian groups, where you can classify everything.
So
you
you
wouldn't have
mean,
discovered this
if I
result.
understand well, any group can be looked as a symmetric group,
Yes.
but
As a
studying them as a
subgroup
symmetric
of a
book
symmetric.
could not be a good idea because when you take the group as what it is and not a symmetric group, it could be much easier to
Yes,
study.
yes. The abstraction makes it easier. Abstraction is a way of making complicated ideas simpler. That's what Dedekind was hoping to tell us, I think. So, for example, composition of functions is associative. And associativity showed up as one of these properties. And so why is it associative? Because of the little proof that you can show that it doesn't matter how you compose functions. And it's a fundamental operation, this composition. You can generalize it to composing binary relations. Right? And binary relations also have associative composition. And the symbol now, due to Tarski, or even before that, Schroeder, is a semicolon. So these things were already studied intensively in the 1800s by Peirce and De Morgan and Schroeder, and then later by Tarski. And so many physical processes can be modeled as relations. This is why we care about this stuff. Composition is used to build complicated processes from simpler processes. So composition is one of these operations with which we decompose complicated stuff into the simple pieces. And one of the best examples is, say, in the design of computer programs, because if you have R composed with S for two computer programs, then it means you first run R, and then the output of that goes as the input of the next one, and you run S, and this gives you a bigger and more complicated program. And there's another very important property about binary relations. You can compare them by one being a subset of the other, which mathematically is just defined as all the elements in the smaller set have to be elements of the bigger set. But what it means is that the relation R is more specific about which elements it sends where. And the relation S is possibly less deterministic. So that's like, these are computer science terms, because software specifications, the documents that describe what a software system has to do, they're written in logic, and they describe this big relation S because they don't need to tell us about what the actual implementation has to do. They just have to tell us what should be true after the program is running and doing useful things, hopefully. And the implementation can have a lot of leeway how to do that. And so you have this idea that you can structure software by using relations and using this ordering on the relations. This will be important when we get to residuated lattices. So algebra, of course, originally was invented to solve equations, algebraic equations specifically, to keep track of how to manipulate complicated operations. But this is a step beyond arithmetic, right? We're talking about ordinary equations with numbers in them. Here's how you solve them. If you have multiplication, you divide. If you have a non-commutative operation, you should also be willing to divide the other way, because this is not necessarily the same. If you want to solve the third equation down there, you have to get the A away from the left-hand side, and so you should put it underneath the B, right? This is the operation of A under B rather than B over A. And you need it if you're doing something with matrices. It's actually part of some packages. If you look carefully at MATLAB, you can do a partial inverse that comes from this side. But if you're working with invertible matrices, there's not much difference. You know where to put the inverse, I guess. Here's the algebra of binary relations. You take the set of all binary relations, that means all subsets of the set X cross itself, or the ordered pairs on X. And you look at composition on it and the identity relation. This is a monoid. It's associative, but it's not a group. There aren't inverses for every possible binary relation. And the interesting thing that drives the theory of residuated lattices is that we nevertheless can solve inequalities. And so if you have a computer program Q composed with R inside some specification S, then this trying to solve the middle one, you know, you're looking for the new specification S over R. This is if you have implemented the second part of your project, because you know you didn't know how to do the first part yet, but then you can divide away the second part and you can figure out what is your new specification until you have that you now have to fulfill in order to finish your program. Right? What's still left to be done?
I think I do not understand. Why the set of all the relation of the set X as not inverse? If you have a relation from a Z and the Y,
you can
the
go
X,
back.
you can write the Xi,
Yeah.
and the composition of that is the identity relation. Identity relation work with identity as the zero
composition
element.
of it will not be the identity relation in general, because the problem is that the binary relation can relate the same object on one side to two different objects, and then when you try to compose, you go.
Okay. It is a group only if the relation is functional.
Yeah.
If the relation is not functional, it's not.
No,
Okay.
they have
Not
to
even
be
then. They'd have to be bijections.
bijective. This was the first example.
be
It's
functional
S sub
both
X.
directions. But they're all the relations, so there are also
Yes.
the rejection.
They're
Sure,
not.
so there are ones that are.
Okay.
that are
Yeah.
inferred.
So the
Okay.
symmetric group of permutations, this S sub X, is sitting inside this monoid, but the monoid is not a group. And on the other hand, this monoid has this nice order, and with this order, what is represented by these division operation looking things here, these are called, S over R is called the right residual. It's the largest relation, which will have this property that when you compose with R on the right-hand side, you still stay inside S. That relation always exists. That's the surprising thing. That the reason it always exists is because the set of all binary relations is a complete lattice. And we'll see more about that. But abstract relation algebras, which I will not define, I will just mention they were defined by Alfred Tarski in 1941. But they were based on these algebras of binary relations, and they have all the nice properties that these algebras have. And an example is coming from this set. But to make a relation algebra, you don't just look at the monoid, you add intersection, union, complementation, empty set, the largest set, which is x plus x, also written as x squared, and then composition identity that makes a monoid. And then you add this converse operation, which is the one that Marco was saying. You could just turn the pairs around, which you can do, but it doesn't give you an inverse. So
is this reductive intersection union complement, is that required to be Boolean? For Tarski's
relation algebras, yes.
for Tarski's definition.
Tarski's relation algebras are Boolean algebras with operators, and exactly the signature. Yes.
Okay.
And what is a poset? Right? It's a set with an ordering relation that is reflexive, anti-symmetric. So these are all properties nicely described in first-order logic, transitive, and so they are easy to comprehend. A meet semilattice is something that can be defined as a partial order with an operation, a binary operation that's called a meet. And the meet just has to have actually three properties, but I made the second one into one. That x has to be below or less or equal to the meet of x with itself. And the meet of x with any other element has to be below that element and has to be below x as well. And this is enough to give you a meet semilattice. These are first order axioms again. But you can equivalently define meet semilattices completely algebraically as things that are where the binary operation meet is associative, commutative, so pretty close to a commutative group now. It's actually just a commutative semigroup. But then you have to add idempotence, and then it becomes a semilattice, a meet semilattice, because I called this a meet operation, but otherwise it's just a semilattice. But there's the connection. You can get the order back by doing this operation between x meet y, and if it always gives you x, then it means x is less than y. Or if it gives you x, it means x is less than y. You have joint semi-lattices, which are the dual notion where you, in the definition, you just replace less than with greater than, or less or equal to with greater or equal to. And then you get a lattice by saying that you have both of these operations, and they give you a meet semi-lattice and a joint semi-lattice with the same order. And I learned this from Professor Moja, because I'd studied lattice theory for many, many years, but I didn't really see this, because I was just studying them algebraically. I was not very much.
Without order.
Yeah, well, with order. You can't study them without order, but I was not, I looked at the algebraic definition of what is a lattice. And so, it's, of course, this is a good way and the right way to look at it. And the posets and semi-lattices, the reason we like to work with them is because they can be displayed in something called Hasse diagram form. Hasse was another mathematician in the 1800s. And here's a picture of all the posets with less than or equal to 5 elements. So you have, that's not even all of them. The top 3 rows you have to also turn upside down. You have lots of such partially ordered sets. The ones at the bottom are self-dual. Here's an interesting question. How many partially ordered sets with 0, 0 being the bottom element? So if the partially ordered set has exactly 1 bottom element and 5 elements in total, which of them are not meet semi-lattices? If you look at what's got bottom elements, these are actually lattices. So both meet and joint semi-lattices. Everything that has a bottom element is a meet semi-lattices except one on this slide. So if you can find it, then you know what you have to look for. But it's cute. There's, of course, many posets with a bottom element that are not meet semi-lattices, but they have to have more elements than 5. Up to 5, there's only 1. And it's sitting right there because that's the configuration in which you don't have exactly a unique meet. Here's the list of all the lattices, up to 7 elements, right? And both of these theories do not have good structure theory, because these lists, I mean, they're nice, to me at least, you can find them up to a point by hand, but being sure that you have them all is hard. That's where you have to do all the work to figure out that there aren't any others with 5 elements. And if you try to even do the 4-element posets by hand, you will probably miss one until somebody points out, hey, what's about this? Or if you know how many there are, then it's easy, right? Because you know I'm still missing one, that's fine. But if you don't, then it's the tricky part.
What's the second index in those pictures? The first one is the number of elements?
Yeah, the second one is just a random number.
It's just an index.
It's increasing to separate the ones that are different. And they're all non-isomorphic, of course, and again, you have to dualize the non-self-dual ones here, because there are lots of such lattices. The definition of residuated lattice is due to Ward and Dilworth from 1939, and it's, now my talk actually starts. You start with a lattice, and you have to have a monoid on it, and then you have to have these 2 ways of dividing in order to solve the inequations. And these are exactly the way in which you would like to solve equations, except then you would get group theory, and here we get something more general. This is studied in this book that I was involved in, which is now 16 years old or so, but it's still, sometimes I find stuff in there that I don't know. Which means that either I knew it at some point, but it's fun. The symbol that we use for the operation is mostly omitted, like the usual notation. Here's another way of studying small residuated lattices, right? Like the lists that you saw before. I used to try and find interesting stuff in residuated lattices, and to enumerate all the small ones is a bit of work. This is a document that has 42 pages, and it says all the residuated lattices of size up to 6. And the second page is page 4, just to show the more interesting ones of size 5, and that's where size 6 starts, and then the rest of them are just of size 6. I believe there's like 1,488, right? And still, I made this list in response to Nick because I was able to get stuff out of software that told me what I wanted to know, but he was like, can't you just put them all on a page? And I said, okay, let's try. And so since then, it's been quite nice to, he said, graduate students go and look at some aspects of these, and then you imagine there should be other ones, greater and bigger ones with the same structure, and you discover stuff. So it's a view into what finite small, very small residuated lattices can look like. The pictures show the lattice structure, but then the annotations on these little dots, there's round dots, there's black dots, they show you something about what the monoid is doing. So if you carefully study this picture, you can read off the monoid. The residuated lattice is commutative if it satisfies this. It's integral if the identity element, which we called E here, is the top element of the lattice. And then it's called divisible if it has this nice kind of property that the y multiplying the under y makes something cancel and just gives you x. Now in group theory this should always hold, but in residuated lattices it doesn't even hold if you assume x is less than y, but if the residuated lattice is supposed to be divisible, then it has to have this property. So that's a restriction, and it's called semi-linear if it's a subalgebra of a product of linearly ordered residuated lattices. I briefly told you what a product is. I don't want to dwell on what a subalgebra is. And semi-linear just means nice. Constructed from straight things that are linearly ordered. A lot of the pictures here, in fact, the majority of residuated lattices are ordered in a straight line. Right? And this is something that you
Sorry, Peter. Can I ask a question? A quick question? I mean, are you going to, I know some of the correspondence to the logic things that of what you're talking about, right?
Yes.
But I have no idea about divisibility or semi-linearity. Are you going to tell us about that eventually?
Yes, a little bit. I won't go into, I'll tell you about the structure theory of the divisible residuated lattices, the finite ones. So that, yes. And whether that means you will really know why it's divisible or not. Bosbach is the person who studied them in depth. And there's surprisingly, divisibility is a big restriction. And he already did this in general before, in the 70s, in some notes that I had, some of which never been published. But these are interesting properties. Let me go back to the slide here. Semi-linear means that the lattice will always be distributive, but it's even more of a restriction than that. And so it's sometimes these are called representable, and a lot of the applications in fuzzy logic have that as a restriction because you want your logical values to be ordered. So that also shows up in the context that you're alluding to. Unfortunately, I can't talk about proof theory today, sorry, because there's not enough time.
Well, thank you.
How far I get. So
Thank
bounded, it means that it has a minimum element, and that element is often denoted by this upside down T, or bottom. And in a residuated lattice, it automatically means you get the top, because bottom divided by bottom is not undefined. Sometimes bottom is called 0, and 0 divided by 0 in residuated lattices is perfectly fine. It just represents the top element. So in a commutative residuated lattice, the operations of these two divisions, under and over, they coincide, and they will usually be represented by an arrow from x to y if x under y is the operation. And this is an implication in logic, and this is the connection to linear logic. And so that's how substructural logic comes into the picture. But like I said, I'm going to stick to algebra here. MV-algebras. This is an example of residuated lattices, and it's a very concrete one because it starts with the unit interval. And the name L infinity, I hope will be clear in a moment. You have the operations of meet and join being given by min and max, because if you pick two numbers in the unit interval, you can always tell which one's bigger. And that's the result of the join The smaller one is the result of the mean. And then you have this dot operation, which is defined as the max of the addition minus 1 or 0. If the addition minus 1 gives you a negative element, then just use 0. So it's a truncated, weird binary operation. And the first thing you should try and convince yourself of is that it's actually associative. This is not obvious and doesn't look like it should be associative, but it's a nice operation. And then you can also turn the unit interval upside down. That's what 1 minus x does. And so this L infinity is a bounded, commutative, integral, divisible, linearly ordered residuated lattice. So it has all these properties that I listed before. And implication also can be created with this tilde operation. And it has additional properties that I didn't list yet, and it will be relevant later. For example, it's involutive. And then L infinity is called the standard MV algebra, short for many values. So that doesn't explain the name L. L is not for lattice. L is for Lukasiewicz, because inside this unit interval, you can take a finite chain of equally spaced rational points, like I wrote out there, and this will be called the n-valued Lukasiewicz algebra if it has exactly n equally spaced numbers. And there's no point in writing them as rational numbers. You can just call them A1, A2, A3. But they behave in a nice way. They give you a nice monoid structure. And now here's what is here's how divisibility comes into the picture. This generalized basic logic algebra concept is called, is by definition just a divisible residuated lattice, something that satisfies that property. And then a BL-algebra, which stands for basic logic algebra, is just a commutative integral semi-linear GBL algebra. So it's a pretty special form of the GBL algebras. And it also has to have a bottom element, which we now will call 0. And then if you define this tilde x as the x implies 0 operation, that's a type of negation called a linear negation. And this linear negation will be sometimes involutive, meaning that if you apply it twice, you get back what you put into it. And that is a nice property because that's exactly what you have to do to get MV-algebras. And so MV-algebras, which you saw earlier on this list together with abelian groups, and which had a nice structure theory, they have a bunch of axioms, but you can also just define them with six axioms that only talk about the binary operation. I didn't write those down. And so they're sort of an alternative to operating on small finite algebras where we actually know what's going on. And then BL-algebras were introduced by Hayek in 1998 in a book to give an abstract framework for what is fuzzy logic. Fuzzy logic is from the late 60s due to Zadeh. It's an engineering area where lots of practical things, but the theory was somewhat lacking, and Hayek was the right person to say, well, why don't we do this in the setting of logic with MV, with multi-valued logic, and there's a very nice book about all of this, the abstract fuzzy logics. So the poset product construction, if you have a poset, which we had earlier, and you have a bunch of algebras indexed by members of this poset, then we will also assume that the non-maximal elements of, let's just assume all the algebras A sub I are both integral, meaning they have a 1 at the top and they have a bottom element, because we're going to use this in a finite setting where there will always be a unique bottom element in the lattice. And a poset product now is defined as something that looks a lot like a direct product, but it's actually a direct product. So you take all the functions small a that are in this direct product indexed by P, but they have to satisfy this condition. It's a logical condition that says the function a, little a applied at j or a sub j, if it's strictly less than the top element E, then that same function, but argument k has to be the zero of the kth component, and this must happen for all j less than k. Right? This is a weird condition, but it pulls out a subset of things from the direct product of all these algebras AI, and the direct product would be easy to understand, but it's not particularly general. When you look at these specific subsets, you get new algebras appearing, and this subset of the product will always contain the constant function here written as E underlined. You can check that easily, and it will have a nice property that shows you that when you look at all the indices, the way they are labeling with these functions, they, well, the interesting part here is this a set of all indices such that the function A, so the function A has results that are strictly between 0 and the identity. This set, the subset of P, will have to be an anti-chain. And so these labelings are sometimes called anti-chain labelings nowadays. And the operations on this subalgebra of the product, well, it's not exactly a subalgebra because of this following property. The join and the meet you do pointwise, so it's subalgebra, it's a sublattice. But and it's also a subalgebra with respect to the multiplication, the monad operation. But when you want to do the residuals, you have to make some little adjustment, which is also based on a side condition. And it's just technical, but it works. And then when you do these poset products, you get something that generalizes a construction that was used long before that. The ordinal sum is just you're stacking things on top of each other. And direct products, of course, generalizes because you can take a chain. If you take the poset to be a chain, you get the ordinal sum. If you take the poset to be an anti-chain, you get the product. And if you apply this poset product construction to residuated lattices, you get a residuated lattice. And if you apply it to integral generalized basic logic algebras, the residuated lattices which are divisible, if they stay divisible, the result is still divisible. And that's not to be expected.
Another question?
Yes.
Another question.
Sure.
Product poset is the product in the category of posets or not really?
No, it's more like it's a type of, it's a sheaf of some sort in over an Alexandrov space. It's just described in a simpler algebraic way here. I don't think it has the, initially we called it the poset sum. Embarrassing, but we had to change the name. So this paper, 2009, it's actually called the poset sum, and then it had properties that were more poset product-like, and the name needed to be changed. But it was the generalization of the ordinal sum. So initially we thought, why not call it a poset sum? But it's better as a poset product. It's not an actual product. It has this very nice property because in this on this slide, we are showing that poset products of MV-algebras are GBL-algebras because all MV-algebras are divisible and divisibility is preserved. And on this slide, we're showing that finite GBL-algebras are poset products of MV-algebras, and that's the structural result. That's the result that tells you that finite GBL-algebras can be fully understood by just taking these, because all the finite MV-algebras are actually the Lukasiewicz chains, the direct products of them. Right? That's all you can get. So similar to the abelian group case. And so that's very constrained what kind of finite MV-algebras you have, and then the way you can patch them together with the poset product, they build all the finite GBL-algebras. And that was a surprise. They also can build some infinite GBL-algebras, and there's more stuff in the paper, but in general, it's a nice structure theory for GBL-algebras, where previously there was a known structure theory for the much more special BL-algebras. The number of finite GBL-algebras, for example, can be counted. Now, here's an example of something that you can construct with 17 elements. You don't need a computer to do this. You're just patching together things over a 4-element poset, and the things that are being patched together are L2, L3, L4, and L5 on top. And then you have to, and this simple example is actually a product in the middle and then an ordinal sum of 3 components. So you don't really need the poset product, but the poset product does all this in one step. And here's how you would enumerate all the GBL algebras. And that's also something you can do by hand, up to size 6. And you can easily count that the reason there are so many chains as residuated lattices is right here. There are 32 chains with 6 elements that give you BL-algebras. And they come from making certain elements here, these possible 5 elements, idempotent or not. If it's black, it's already idempotent. If it's not yet black, you can choose it to be an idempotent. And there's exactly 32 ways you can choose black dots there. So this product is able to tell you these things, and the structure becomes clear. What the pictures we're looking at here are the poset of joint irreducibles in certain distributive lattices. I'm sorry I didn't explain joint irreducible, but that's how it works. A finite GBL algebra is subdirectly irreducible, which is another concept that we don't necessarily need, but it is connected to this joint irreducibility. If the poset of joint irreducibles has a top element, so you can see in this representation whether something is subdirect or not, subdirectly irreducible. It's very similar to Heyting algebras. Of course, the point here, I guess, is to somebody in logic, you can say that poset products of 2-element Boolean algebras are just Heyting algebras. And therefore, GBL includes all of intuitionistic logic and vastly much more. It includes MV-algebras and Heyting algebras. So we have these subdirectly irreducible BL-algebras. We have a way of counting them up to by, this whole table you can do by hand. That's the difference. And even though there's big numbers on here, not really big, but it's possible to do something like this by hand because you have a structure theory. Let's switch to something else now. The second topic in 3 minutes.
We were 5 minutes late, so.
Yeah, that's,
got 8
we have 10 minutes maybe, I don't know. I'll go a little over time. Sure. Residuated poset is a structure that leaves out the lattice part. It's much more general. You just have a set with the ordering relation and the monoid operation, and then you have this residuation property, which is a perennial, this is the important aspect. This is the restriction that makes these objects more like groups, and therefore there's this possibility that you have a chance to understand the structure, because if you don't have some restriction, the monoid, even the ordered monoids are worse than monoids. Than monoids with all possible types of orders. So the ordering will be, the multiplication of the monoid will automatically be order preserving. That's what the residuation restriction gives you. And you can assume that for ordered monoids, that's usually an assumption, but the residuation restriction gives you much more. All groups are examples of residuated posets. This is when you take the ordering to be the anti-chain order, so just equality, nothing is comparable to anything. And then the divisions are just the standard terms. If you want to divide by x, it's the same as multiplying with x inverse. And you have to do it on the correct side because we don't want to assume commutativity. Or you can look at partially ordered groups. That's a large class of mathematical objects that have been studied. They are all, that's a subset of this much larger class of residuated posets. Or you can look at residuated lattices. Just ignore the fact that you have lattice operations. They're also residuated posets. Residuated posets have some nice properties that they don't all have them, but we could study the ones that, for example, are square decreasing. Or we can study the ones that are positively singleton, which means being bigger than 1, which is called positive in our area. Bigger than 0 is not positive. Bigger than 1 is positive. And if you're bigger than 1, if you have to be 1, that means that the number 1 or the element 1 is a maximal element. That's called positive. Or you can be idempotent, which is a huge restriction and very interesting. And then you could be integral. And there's some connections between them that are obvious, easy to check. And for example, every group ordered by equality is positively singleton because nothing is above the identity element or anything else. Here is some information about how these properties are related. So if you are a residuated poset, there's lots of them of size 6. If you are a residuated lattice, there are fewer, like 1,488. And there we know a little bit more. Square decreasing is a fairly big restriction. Positively singleton is even more of a restriction, surprisingly. Integral is a huge restriction. Idempotent is a restriction. Commutative and idempotent is making things maybe manageable, who knows? Idempotent and integral. Wow, now it's getting to the point where you force some properties on these structures that make them sort of manageable. Commutative here just means the multiplication is commutative. And the question is, can we find good structure theory for some of these classes? And what do we mean? Right? We mean exactly this. In the rest of algebra, good structure theory looks like this. The numbers stay extremely small. Right? All finite fields are easy to classify. All Boolean algebras, there's only one of size 2 to the n, so they're very sparse. But BL-algebras, we just showed, they have good structure theory. Right? And distributive lattices, well, I mean, up to a point, they have good structure theory because posets don't. And there's a one-to-one correspondence between finite posets and finite distributive lattices. So you have to take all this with a grain of salt. But note that all these are commutative. Here we have some interesting non-commutative classes. Again, partially ordered monoids. Oh, this is the first time I'm showing you. Partially ordered monoids are wild, right? It's even much bigger number of them. With 3 elements, you have 109. There's no way you're going to look at them and see some kind of interesting way in which they're related. But for residuated posets, it's now looking relatively tame in comparison, right? Maybe we can do something. And here, yeah, this is...
But sorry,
yes.
Possibly this is clear, but not for me.
No.
What does it mean, the blank? The blank means that you cannot calculate.
Haven't tried.
That we do not know.
I don't know at the moment. Some of these numbers, when they get calculated, they get put into the online encyclopedia of integer sequences, and then you can look them up.
But the blank simply means we don't know.
We don't know, but we could.
You do not know.
I don't know if I leave it blank, but I could probably calculate 5 and 6, but it gets hard. And you can only do it with a computer, for sure. And so there's no structure theory in my definition, which means if you can do it by hand, up to 6 or 7, you probably have structure theory.
This depends on the fact that the number is big.
No,
or it's possible that we cannot calculate, but in fact it's not so big.
Yeah, the number is hard to calculate, is what it means. It doesn't necessarily have to be big, but one thing that makes it hard is you have to eliminate isomorphic copies.
Okay.
And when you get past 12 or 13, the number of possible isomorphisms is pretty big. So for posets, the number of posets have been calculated up to size 18, for example. For lattices, up to size 20. A student of mine did this once 10 years ago or so. And he now works for Google because they deal with big numbers. But yes, that's the difficulty, right? That it becomes computationally hard and we don't know how to do it. But that doesn't mean that big numbers automatically have to be hard, because sometimes these numbers could be big, but they could be like a power of 3, and you could just go and write them down.
So on each row,
yes,
using a computer, you would calculate it the same way, right? It would be what you said in removing isomorphisms or something.
Mm-hmm.
On a row, the method for calculating is the same.
Yes, okay. Yes. And then on the next row, it's similar too, but it doesn't need a new program. It's it uses some software that was created by Bill McCoon. I used to write programs for these things back 20 years ago, and that's how the GBL-algebra structure theory actually started. I did some calculations on the computer and I saw, there's only very few of these things. And so then you wonder why.
Okay, with the blank with the BL-algebras? Because that's supposed to have a good structure theory, right?
BL-algebra blank. Yeah, I mean, I didn't bother to do it. I guess now to say that it's blank is just me being lazy. And it's not that you couldn't fill that in. You're quite right. You're paying attention. It's an interesting challenge, but it's not necessarily hard. Right? It still has to be done carefully because you want the number to be correct. And I don't know if I can do 9 by hand. I said up to 7. So,
No, sure. I know it satisfies your criteria. I just wanted to
I'm
know
being
why 9
honest.
was blank.
But I'm sure you could fill that row. It hasn't been done. And this distributive lattices row has been done up to size 50, and you could go beyond, but not necessarily much. I think I went to 70 once, but it's recorded up to 50. Oh no, the 70 was for something else, but it's related. So the point is that, yeah, the blanks we need these numbers just to roughly compare things, I guess, and to get an idea what's going on. And then we can look at the models, right? The interesting thing here is that the small examples, or if you look at all 3 element models in a theory, like here, the residuated posets with cardinality 3, there's 5 of them, and they are all important. Except the last one we haven't even looked at, studied. Right? It should be studied. It's interesting because it's a poset that has 2 not connected pieces, 2-element part and a 1-element. And it has some applications, but I'm not exactly sure which applications I would recommend here. The structure there's only one of them. The other ones, the G3 is the Gödel algebra. It's got a nice logic behind it. L3 is the Lukasiewicz logic that has 1/2 in the middle. And Z3, I mean, that's an important group, right? So this 5th one should be studied. And the next 28 are a little bit much, but we can still kind of see them. That includes 2 groups of size 4. And still, there's no structure theory. So it's not good to look at this for too long, because you may not discover anything general. Can residuated posets be built from certain components that are simpler, maybe? And in some cases, yes, from some so-called local components, which we want to identify, and we call them A sub something, where this should index them, and there's maps between them. And so the construction that gets used here is called the Plonka sum, and I'm going to go through some details in a relatively blasé way here, so sorry about that. But we reconstruct the order for involutive residuated posets if we can impose a few more restrictions in a surprising way. And this research started in 2019 when a graduate student, Olin Todd, from the University of Bern, he was working with George Metcalf, and Diego Valota was a postdoc at the University of Milan. They came here on a Sysmex research grant, and we studied these things for a month very intensively, and then we kept corresponding about this. And finally, we saw that the involutive idempotent residuated lattices, the finite ones, the commutative ones, well, they all happen to be commutative, are actually something we can understand. And that was like, wow, I kind of suspected it from some calculations that I'd made 5 or so years ago before that. And I had it on a list of things that one should look at. And we used this Prover 9 Maze 4 software extensively. It's a first order theorem prover and the first order model finder. Both of them were very useful and necessary to get this project off the ground. But in the end, of course, everything was proved by hand and checked. And so what is the story? Well, now it's been generalized to involutive residuated posets, which in the paper where this appeared earlier this year, this is joint research with José, Gil-Férez, and Melissa Sugimoto, and Sid Lodia was an undergraduate here that was involved in the early stages last summer. And so it all came together in something that is another version of what was done for finite involutive idempotent residuated lattices, and now is being done for these things called involutive residuated posets. They are just a poset with a monoid and with a new, simpler condition, which is called involutive negation, Einheck, and 0 here is the minus of 1, and that's the same as tilde 1. There's these two linear negations, so this is a type of linear logic, but without the join and meet, and all groups are in this class, all MV-algebras are in this class. Actually, directly, the lattice operations are definable on MV-algebras. And you can also see that this class of involutive residuated posets, in RP is the abbreviation, is equivalent to residuated posets that were defined earlier, which satisfy this nice property here, that the negations have to cancel each other. The two linear negations cancel in both orders. And this involutive negation is just a simpler version of residuation. That's what this slide is saying on the fourth line. On the fourth line, we have something that mimics residuation, and you can make it exactly residuation if we define these over and under operations in a nice way. And then we have something that is, well, that shows that the multiplication has to be order preserving in both arguments. So these are all nice properties, but they don't tell you much more about the structure of the monoid. If you, in addition, assume that it's integral, then you also get that it must have a 0 that is at the bottom. The 0, of course, is the negation of the 1. And here are the three properties that we identified in this project. This goes back a few, maybe like a year and a half now. It's called locally integral. So the first one says that the minus and the tilde have to be related in a certain way that gives us that x under x is the same as x over x. And then we have to be square decreasing. That's a very big restriction. And also we have, everything that is below the 0 has to be idempotent. That implies that everything above the 1 will be idempotent. And so one result is that if you are integral, then this is already true. All these three properties hold. If you look at the positive cone, which is all the elements above 1, then you can see that this element x over x is very special, and it behaves like a local identity element. And so we called it 1 sub x, and the negation is 0 sub x. And so it produces a way of identifying these local components. They are the equivalence classes of this equivalence relation. No details given about how that all fits together, but this is basic discrete math. And then you can say that, oh, wow, these components interact well with the positive idempotence, or all the elements above 1 are idempotent. So the components interact in a very nice way with the positive elements. Each component intersects exactly with one positive element, so we can index the components by just the set of positive elements. And so from a locally integral involutive residuated lattice, we can obtain components that are themselves integral involutive residuated lattices, and then we can make them into well, those are the components, the integral components. And we can see that they have to be there in every one of these locally integral NRPs. So this is sort of a diagram of what these things look like in general. And then we can prove a few properties about them, which are not going to be of great importance right now because we're already 15 minutes after. But we can use something called the Plonka sum to patch them all back together to the structure that we originally started with. And that shows that you can decompose locally integral involutive residuated posets into integral ones. And if you understand all the integral components, you will understand the structure of the whole object. And that was, again, something quite surprising because here's how Plonka sums work. You take the union of all the components. It's not a product this time. It's really a sum. It's a disjoint union. And you are obliged to have an operation for all elements in it. So if you want to know what it means to multiply an element in one component with one in another component, you first have to shove them into the same component using your functions, these phi functions that are homomorphisms between the components. And that means you can build these things. There's some details that have to be checked. All of this took a huge amount of work, and the absolutely amazing contribution by José was that he figured out something that we hadn't been able to figure out for, like, I don't know, 4 years. Just turned out to be the right idea, and it works. And it's exactly how you define the order. After you patch them all together, the order on them is not given by the Planck sum, and it needed an observation that was quite non-trivial to show that it really works. And so it's wonderful. We have this theorem that we can do this. It's a structural characterization of these results. And if the components themselves are easy, then we can get a full understanding of these mathematical objects, because then we would understand the components. And the best case is when the components are Boolean algebras. Then what we're building are idempotent, involutive, residuated posets. And so we understand the structure of all of those now because they are built from Boolean algebras by taking the disjoint union over a particular poset. Could be any poset. And it has to satisfy some conditions which are enumerated in some further work. Here's what this roughly looks like if your poset has 4 elements. You have 4 components stacked together. And we have this notation for the Planck sum and conditions that it has to satisfy in order to be something that you can glue together into a proper residuated poset. And then you can construct finite things again by hand. Here's a list of them. This list even includes the ones that do not have an identity element, because one of the recent things we've done this summer and the last couple of months is to show that the same theory works with semigroups, not just with monoids. So it works well. It's characterized by some nice properties. These properties can be simplified a bit. This is the final result that tells you when you can do this. The components don't even have to be finite. The poset doesn't have to be finite. The resulting structure, of course, wouldn't be finite then either. And it's quite general. It should, you can do fun stuff with it because you can build things that are otherwise not easy to see. So here's a way of patching together infinitely many 4-element Boolean algebras in a structure that from one point of view will look like this. This is not the lattice structure. It might look like a lattice, but this is a view into the monoid. The monoid here is associative, commutative, and idempotent. So the monoid already forms a semi-lattice and looks like this and was built in this way. The identity in this monoid is at the top because it's thought of as a meet semi-lattice. The picture here comes from Siena. I gave a version of this talk in Siena with the new results, and the piazza in Siena has this picture of it has these bricks. It's constructed like this, and it's my original results of GBL structure also came when I was in Siena. This is something amazing about Siena. The city is full of interesting patterns. This is what it looks like as a lattice. When you shove this thing together, you get this nice fractal structure of a lattice with the identity sitting in the middle. It's an infinite countable lattice. It's one generated, which is the surprising thing. And this is a picture of the pattern in the Duomo of Siena, which is strikingly similar. And there's a couple of questions we can do. This transitivity condition is a global condition and can be replaced by some simpler conditions, which recently got simplified even more because this whole thing that we're discovering is simpler than we originally thought. And simple doesn't mean it's easy to find. It just means it's easier to understand. The locally integral involutive residuated posets, if it's idempotent for all elements, then the integral components are Boolean algebras. We've looked at this case now with the partially ordered involutive semigroups, which is not any more complicated. So that's surprising, because we can always add an identity element to semigroups to make them into monoids, but this isn't true in the ordered setting. An ordered semigroup cannot be just made into a monoid by adding an identity, but in this setting, we understand the conditions when you can or cannot do it. And so there's some questions: under which conditions is the algebra lattice ordered? Are locally integral involutive residuated posets or involutive residuated lattices decidable? This locally integral was these three conditions. They're not super complicated, but we don't know if they have a decidable equational theory at this point. This is the current preprint that's on OCIE, just got submitted a couple of weeks ago, about the semigroup setting. And this is a view into Tuscany from Umbria, where I was visiting a friend of mine in the summer, and
Which is the Trasumeno?
it's near there, yes. It's
The lake here.
Yes, I believe so. I can tell you the exact name. I don't actually. I can't verify that.
I
Sorry,
think it is
but
the Trasumeno.
could be. Yes, it's a beautiful area, and I really enjoyed working on these ideas. There's now efforts also to generalize from where we know what's going on, which is the involutive case, to non-involutive structures, and that's what the research there was aiming to look at. So that's it. Thank you very much.
So the first one that tell me again that the talk in philosophy has 1 hour and a half, the talk in mathematics are 35 minutes. I have an example to contradict.
Yes.
Okay, questions, remarks.
So, for
No, you go, then you want.
There's somebody in the chat.
Oh,
I saw that somebody said
Yeah,
that.
somebody.
Oh, okay.
Five of you.
Please.
So in for the group theory is the groups are acting on geometries, the group of congruences, and that allow Felix Klein to come up with that brilliant idea, Erlangen program.
Yeah.
Can we talk? I mean, is there anything like way of for lattices to act on sets, or because there is this algebraic structure that's very rigid, and there is correspondence with geometry, with topological spaces, possibly allow introducing actions.
It's the notion of value, right?
yes.
Is similar to.
There are some in the setting of MV-algebras. There's definitely this is connected to probability theory, and you have these ideas of
States.
states. Yes. So there are these actions. They are a special kind of homomorphisms into, say, the unit interval, and so it's possible. I don't know exactly how to describe the question is a very good one. So I would like to be able to say I'll get back to you. And
You mentioned, that you have these numbers and so on, and the very, the concept of actions will give you a structure there, a way
Yes.
of ordering them from something that's more important to something that's perhaps richer.
the issue is that I've talked mainly about finite things, and finite linearly ordered sets have no permutations. The only order preserving map is from a finite chain onto itself is the identity map. And so,
But it's exactly that. Take, for example, a square, the rotations, the symmetries, and so on. That
Yes.
corresponds to a group and so on. It doesn't have to be complicated.
no, I agree. And these the poset product, for example, will have some, the automorphisms of the poset product is something that you could study with that point of view. And in fact, personally, I like to, why are posets interesting? You can draw pictures of them, which means you can do geometry with them. People do the Mobius functions on posets and on lattices. These things work. And so there's definitely a lot of combinatorics, there's a lot of geometry, and this is only beginning to get explored in this area, I think. So there's huge potential for these ideas to be translated, yes.
And also, you mentioned Alexandrov spaces.
Yeah.
What's your definition of Alexandrov space?
It's the topology that comes from taking a partially ordered set and viewing all the upward closed sets in it as a topology. And
I will tell you more later why.
yeah.
Yeah, but there's more than one use of that name.
Sure.
There's a
Yeah.
different Alexandrov space, but yeah, for post sets, this is the standard terminology.
I admit I didn't know the one.
Yeah.
Yeah.
Other questions?
On chat.
Sorry?
Ah, yes.
No, we
Chat.
looked on chat and-
Peter, I have several questions if you can answer them.
I'll try.
First one is, could you go back to the periodic table?
Yeah. Let's see what that is. There's lots of slides here. Now my clicker stopped working. That's not good.
Right.
Okay.
My question on that one is, why are the Lie algebras appearing there?
They're not Lie algebras, they're algebras of Lie type, and they are the finite. I don't really know Lie algebras very well, or Lie groups. They are groups of Lie type.
It's
that
before that question.
are the property. The reason they appear there is because they are simple. So this is
You passed. Yeah.
finite simple groups, right? So this is the classification of finite simple groups, and the vast majority of them come in these families of simple groups of Lie type. And there's people in this room who can explain that way better than me. So sorry, I have to punt on that question, but they are matrix groups. They are groups where you can show that they're simple. For example, on the left-hand side, the green ones are the alternating groups. The yellow ones. The yellow ones are the alternating groups, and they are obviously simple, but they are just the maximal non-trivial subgroups of the symmetric group. And
Thank you.
yeah.
Then do you mind going to 14, slide 14?
Slide 14?
Yeah. 13,
Good.
14.
14.
Yeah. You kind of teased us. You said that there is one that is not, and you didn't show which one.
Oh, I was pointing at the screen. I'm so sorry. It is P5, 15. And I wasn't visible because I made the camera to be in the middle of the board, and all I ever draw was this.
Super, thank you. I was kind of feeling a little bit miffed that I didn't tell which one.
So it's P5 to 15 now.
I got it now.
The 5 by your.
My other question is a little bit later again. I don't remember exactly which slide that is, but it's about this correspondence between finite GBL algebras and abelian groups. Is that just an analogy, or can you make some sort of morphism, sort of a description of that?
Finite abelian groups and MV-algebras do not correspond, but the table that I had makes it look like they would. They both have this interesting property that if you take products of two chains, products of two MV chains, another MV algebra, and that MV algebra has no other subalgebras. So it's easy to count them. There's no skew subalgebras that show up. In group theory, it's a little, there's a little bit fewer groups. So you can see, for example, in this list here, you have abelian groups, you have MV algebras, and they almost correspond. But at number 6, there's one abelian group, but there's two MV algebras, because the L2 cross L3, it's an MV algebra, and it's different from L6. So there's a structural difference, and it's not a categorical correspondence. The categorical correspondence is between MV algebras and certain, I mean, it's the integers, really. The MV algebras come from intervals in the integers by Mundici's factor.
Mundici's theorem is that the category of MV algebras is equivalent to the ordered ordered abelian groups or something.
It's abelian groups with a strong order unit.
Yeah.
And so you have to take the the integers together with one element, and that
I see.
it can be any integer, and that will represent a strong order unit in the integers. So MV-algebras are really intervals of integers with the appropriate operations defined on them. And then from an MV-algebra, you can get the integers back. And this correspondence is Mundisi's functor. And for the linearly ordered, but of course the functor works for arbitrary algebras in these categories.
Right. Thank you. I still have another two. If you, if I did not. I mean, that's just clarification because I missed the bit about the product poset being some sort of having some sort of connection to Heyting algebras.
Yes, this was I should have elaborated on this because I promised it in my abstract. So Heyting algebras are subalgebras. They are not subalgebras of Boolean algebras, but they can be thought of as, I mean, as the distributive lattice reduct of a Heyting algebra, of course, can be embedded into a Boolean algebra.
Right.
And the poset product gives you one such embedding, and then it tells you how to restrict the Boolean negation in such a way that it gives you the intuitionistic negation. And that's how poset products of two-element Boolean algebras turn out to be Heyting algebras. And this is really just this is an observation about the finite version of Isakia duality. The infinite version has something to do with Isakia products that are in another paper that tried to generalize poset products into objects that have topology.
Right. So my last question, I promise. So then, you know, the thing that I'm trying to get at is this business that when you think about this involutive residuated posets, you have this two notions of negation on them, right?
Yes.
One that is coming from thinking of the commutative implication. I mean, commutative because you take the residuation and kind of make it a single implication. So an implication into zero. And the other one that I thought was coming from the order inversion. And then you kind of smash them together. Is that correct? Or am I imagining too much?
Yeah, I think the minus and the tilde are both linear negations. They come from non-commutative linear logic because we don't assume commutativity in the setting of involutive.
But you do assume commutativity by the fact that you're saying that there's only one residual implication, no?
Yes, if we have the arrow, and in particular when we're dealing with finite GBL algebras, they all turn out to be commutative. So this divisibility condition forces your monoid to be commutative, right. And at least in the finite setting. And then you have this one type of residual that you write as a logical arrow. And from that logical arrow, you can construct the tilde if you use, it's the linear negation. But if you do this in a GBL algebra, it's not, if the GBL algebra happens to be a Heyting algebra, it will give you the intuitionistic negation. And if the
and then you add an extra condition, right? Because then you add this business of the tilde followed by the minus.
Yes, that's the involution. And so that's the condition that forces, I mean, in the commutative case, it would just mean that tilde and minus are the same. So that you're in a cyclic setting, but also the tilde now has to be the identity function. Now that normally in intuitionistic logic, that would give you Boolean. But here it just gives you MV.
Right.
So Boolean logic is a variety of MV algebras. It's a extension of,
Right. Well, great. Yeah.
So GBL algebras have a lot of nice logics inside them. That's one of the takeaways. But of course, residuated lattices have even more logics inside them because they have all substructural logics inside them. So maybe that's too big. I mean, for a lot of people, when they say residuated lattice, they actually mean integral, bounded, commutative. And we try to avoid that because most of the results that you can prove in the integral bounded commutative setting are actually also true in the more general setting. We just need to discover them and prove them.
Right. But I mean, if you are like me, so much more interested in the logic, it does make sense to take the commutative case,
of course,
because
yes.
you want the same
Absolutely.
single
No,
implication.
it's, I mean, sure.
It does not make sense to take the integral just means having a unity, right?
Integral means having the unit at the top.
Okay, so that's the one that doesn't make much sense for a linear logician, because you'd
Right.
expect to have
Yeah,
different ones.
Yeah,
and,
no, that.
And the bounded, sorry, what was the third condition?
Bounded,
Commutative integral, these are usually.
bounded commutative integral. So bounded in linear logic, you often have the bounds anyway. So
Yeah, but that's not the part that we are interested in, because the bounds then are just empty and 0 and 1, the adjectives, right?
Yeah, they're additive.
yeah.
So I'm not so interested in that. But so the other, I mean, there is one still bit that I'm missing, because I think so what I'm saying is that I'd be interested in the residuated posets that are commutative, and then you're trying to tell me that I should think about the involutive ones, because they are the well-behaved ones, right?
Yes, absolutely, and it's a type of
Cool.
it's a generalization of linear logic where you leave out the lattice operations.
Right. Okay. Thank you. That's
Sure.
very, very exciting. Very exciting. Thank you.
Thank you for
Other questions?
I saw an integral symbol.
Yes, I'm sorry, things got very fast at that point, and I apologize to my co-authors.
Raced by and I was intrigued. I didn't know what it was doing.
It's a way of summing up all these components, and it's actually used in category theory in that setting. It's when you see integrals in category theory, they don't mean the integrals of calculus, but they could.
It's something analogous.
Yes.
Okay.
Yeah,
Other
they're meant to be analogs of some kind of summation process.
But in this case, it's very finite. I mean, at least in my world. In the setting, it was also able to sum infinite things, and possibly we could try and figure out if it could be an actual integral in some settings.
Right. But even in the finite setting, you wouldn't want to replace it with a summation sign, because that would suggest it's just a disjoint sum.
Right.
Because that's the standard notation for disjoint sums.
Yeah.
So it kind of needed a different symbol for this.
In some sense, this is a disjoint sum, but then an additional
with
structure comes
right.
because we're in a very nice setting, and this additional structure makes it much more useful. Yeah.
I have just a comment, and it is that in those cases in which Peter was saying that we have a very nice structure, or we could expect to have a very nice structure theory, because looking at the numbers, we see that the numbers don't grow that much. It is also interesting to see that in many of those cases, the numbers are not increasing always. So we don't have sequences of increasing numbers. We have, for example, for MV-algebras, we have 1, 1, 1, 2, 1.
That's a good point.
1, 3, 2.
But that is, I wanted to make the same observation, but it seemed to me that not all the tables are like this one. There are another table that you have, I don't remember in which slides, one of the last slides, in which it seemed to me that it's not true.
It is not true, yeah. It is, that in many of
I made the same observation, but then I found one that apparently is not true.
Yes.
These sequences are called.
This one, the first one. This one. This one, for example, the commutative idempotent is nice, but this is increasing. They're all increasing.
Yeah, and this one they're all increasing. The last one is actually the one from distributive lattices.
So even the last one that I don't know what it is, the Boolean algebra, of course, but that's the Boolean algebra I understood. But also the idempotent integral, that is very simple structure, very simple.
Look,
it's increased.
This is an invariant for this class. These numbers are this class, and if you go higher up, distributive lattices, it's the same numbers. And so you can say that there's something going on here, and it's totally correct. The idempotent integral residuated posets are in fact Heyting algebras, and finite Heyting algebras are distributive lattices. And so this is
But they are the same up to 2, 8, or are the same in general?
they are always the same.
Always the same.
Just, yeah, that's a theorem, but you notice it when you look at this, and so you know, since distributive lattices and Heyting algebras have been studied for decades, centuries, you can now ask, why is this true? Right? And that's how some of this was discovered, because you notice things are much nicer than you expect looking at the axioms that you've imposed.
I have a more philosophical question, if you want, because it's my job. You started with a quotation by Dedekind to say that what is fantastic doing mathematics is to find some structure that is invariant and that can explain a lot of phenomena. So if I look at this phenomena from an internal point of view, of course, there is a lot of interest because there is a lot of curiosity to find the structure, etc. But if you look at this from the Dedekind point of view, so what are the invariant that all these algebraic structure capture? So you can say that all these algebraic structure capture some sort of mathematical invariant, as it happens for group, for rings, for field, or for vector spaces, or no, or simply you are not interested in that, or
I mean, what invariant do you?
Like I said, in groups, the groups you can apply group very well in mathematics. Mm-hmm. So it's an invariant structure that you find in algebra, in number theory, in geometry, and the same for vector space. Vector space is a structure that you find practically everywhere in mathematics.
Yeah, but posets are also something you find absolutely everywhere.
Okay, poset
and that's the beginning of this.
Yes.
So you have symmetry, which is group theory.
Yes.
And you have immediately subgroups. So you also have partial order. But that's a different kind of, it's not really invariant. It's a different kind of structure. Invariance is what group theory is meant. I mean, that's what it's built for.
No, but
right?
I showed the relation example, right? These relation algebras that Tarski defined are structures that show up because binary relations are pervasive in mathematics.
Right.
And how you handle them, the general properties that they have are captured by properties of relation algebras. And the residuated lattices are generalizations of it. So relation algebras have operations that give you exactly a very special kind of Boolean residuated lattice. In that sense, the residuated lattices inherit the invariant from the relation example. Right?
If I may interject too, Peter, I agree with you that the thing is a group has always a form of implication given by the inverse kind of, you use the inverse to create the implication of a Heyting algebra. So you are back to the situations that you kind of had before.
Yeah. Actually, one of the motivations to study residuated lattices from the beginning was to study the lattices of ideals of rings. Yes. Every lattice of the ideals of ring is one of those residuated lattices.
So in many cases there are
and then
a structure that is captured by that.
And then residual lattices are exactly the semantics of substructural logics. Okay. So the residual lattices come from many different places, and the fact is that the property of residuation corresponds to the property of adjunction of functors, which is everywhere in mathematics.
Again, yeah.
Okay. And another question from someone that is really external to us.
Actually,
you insisted you were only speaking of finite structure. And what is the interest to study, if there is an interest or not, and if yes, what is the interest to study infinite example of the structure?
There is an interest, and it's the reason I looked at finite ones is because they're easier to draw and explain. But the results I mentioned also work for infinite structures in many cases. That one has to be more careful. Sometimes you have to involve some topology to make things work. So it's technically more challenging, but also much more where mathematics excels, because if something works well at the finite level doesn't mean that it will lift into the infinite realm, but these techniques do. And this has been well studied for a long time. I think, for example, you can ask in abelian groups, if we really just want to study the integers, why study these cyclic groups? Right? Aren't they just a distraction? Or why study abelian groups axiomatically instead of just studying the integers? I mean, number theorists really just study the integers, but what do they use? They use modular arithmetic all the time. They have to. They use the finite fragments of their theories because that's how you discover interesting connections between things and solve problems. And so this interplay between the finite and the infinite is extremely fruitful. And that's what we try to do. But how do you do it? You try to find these classes where you can explain the structure of something, but the axioms that you choose a small list of nice looking axioms, but the class is still completely wild. So you add more axioms, you bring it down to something that is so small that you can now understand it, and then you start peeling off some axioms and try to also explain the bigger ones. And each time you can try the finite ones first, but in some situations there aren't finite models. Lattice order groups, there's one element lattice order group and the rest of them are infinite, so you're out of luck. Doesn't mean that we don't study them. We study them a lot, but we have to use other techniques.
Okay. So thank you, Peter.
Thank you.
Thank you, Valeria. Bye-bye.
Thank you very much, Peter. See you. Bye.
See you, Valeria.
Thank you.